Okay, so now let me invite to the stage Tomasz, who is going to deliver another one of technical deep dives of today. And this is going to be about something that's dear to me because of the way I perceive my personal freedom. And I think outsourcing everything to the data center in US East 1 is probably not the best choice for the things I want to personally use. And Tomasz is here to help you build things that I would like to use. So for my personal benefit, please listen to Tomasz now.
Okay, I'm going to start with a question. How many of you here are working on web apps? Quick show of hands. Okay, the majority. Awesome. So imagine you are working on a web app. You ship it to production. It's quite good, so you actually have real users. And these users love the app. But one day, some of these users come to you with the following question. Hey, I really like the app, but can I use it without the access to the internet? And you freeze, absolutely terrified. You think to yourself, well, this is a web app, it just doesn't work without the internet, right? What do you do in that case? Do you have to rewrite it as a mobile application? And the answer is no. Web apps can still work offline, and this is exactly what I'm going to be talking about today. My name is Tomasz Gil. I'm a senior software engineer at OpenSpace, and today, based on a real case study, I will explain to you how to add offline capabilities to web applications. Quick bio slide. You can scan the QR code. It will take you to my website with all the links there. So let's connect, reach out, and say hello. And I will start with a bit of story and context. So OpenSpace, the company I work for, is a visual intelligence platform for builders, so construction industry. We help teams track progress, compare work against plans, and spot issues. And one of the important pieces of information we store in our system are field notes. And this is going to be important throughout this talk. Field notes are actionable, localized, and time-stamped pieces of information typically related to something that needs attention on a given construction site. They might say, here's a wall that needs to be repainted, or like in this example, there is a broken window on 3rd floor that needs fixing. So we shipped an app. You open it, you can browse your field notes, works nice and fast. That is until someone tried using it on an actual construction site when this happened. No internet, the app is dead, you can't use it. So it turns out construction sites can have very, very poor internet connectivity, even in the middle of large cities like Warsaw. It's important for us to ship software that works reliably, and especially around field notes, since they capture information about the site. In other words, it's great if you can see and update your field notes from an office with high-speed internet, but where you need this data the most is in a construction field. So all of that made us realize that we really need offline support. And a question that followed was, again, this is a web application. It doesn't work without the internet by default. That's typically what mobile apps do. Do we have to rewrite it as a mobile application to support the offline use case? As I already mentioned, the answer is no, or at least not necessarily. Because offline support is a set of capabilities, not a platform decision. And I hope to prove it throughout this talk. Here's what we'll cover. So first, we will choose the correct offline model for what we need. Then we'll make sure our app can load offline. Then we will discuss persisting data locally, and finally handling offline changes. So far, so good? Cool, awesome. So let's start by going to our builders for just a second. They probably don't know it, but the app that they are using is a single-page web application built with TypeScript, React Query for data fetching, and built with Vite. Very, very standard web technologies. They don't need all of the functionalities to be available offline, but they do need two things. One, they need to be able to view the field notes they previously saw. And two, they need to be able to update the field note status. Okay, two things. And lastly, sometimes they do have good internet connection, sometimes they don't. Let's call it 50-50, roughly split. And these are our technical background as well as the product requirements that we will try to satisfy. So there are two main offline support models we can choose from. And one, that's offline first. And in that model, we take all of the data that we need, we store it locally, and we think of that as our source of truth, meaning we always read from this data, both online and offline. We always write to this data, both online and offline. And then continuously, periodically, we take that state and sync it with our server. The result is we get the same exact experience both offline and online. And this is a powerful model because everything happens instantly, so the UX is great. The downside, typically quite complex to implement and requires both front-end and back-end pieces to pull it off correctly. And on the other hand, we've got online first model with an offline fallback. That's a more traditional model where we still think of our server data as our source of truth. Reads happen from the API first, and we only fall back to local data if network is not available. Writes, similar, API first, falling back to local data if necessary. And finally, sync happens only once, and that is when the user goes from offline to online. The result, the user experience is typically a bit more limited and constrained, but good thing is that this model is, on average, easier to implement. And speaking about user experience, this is a great question to ask yourself. What user experience do you want for offline actions? Do you want to show the result of an offline action as if it happened and then sync later? You probably want to go towards the offline first model. Or do you want to show the result of an offline action as pending and then replay later? Then you probably might be going towards the online first model. And for us and for our builders, we chose the second option. So the online first with an offline fallback model. And here's why. We only need offline support for a single action. So the complexity that comes in with a full offline first model isn't really warranted. We do want the transparent UX. So we want to say the changes are pending because that's what they fundamentally are to us and to our users. It fits very nicely into our current architecture. There is not much rework needed. And finally, as long as we can accept last right wins strategy when it comes to concurrent updates, we can get away with no conflict resolution at all, at least in the first iteration, and that drastically simplifies the solution, pushing most of the complexity to the front end. And that's the model that we've selected, the online first with an offline fallback. And on a technical level, that translates to the following. Our app has to be able to read data from local cache when the user is offline. And two, it has to be able to write any updates to a local queue that we will replay later when the user reconnects. And with that out of the way, let's now make sure that our app can even load offline. And we have to start where we're at, and that's the default browser behavior. I bet you've experienced it at some point, but let's go over that real quick. So you open the app, it loads successfully, then the network disappears. Maybe you're on a train or on a construction site for that matter. You try to refresh the page. The browser tries to refetch index HTML. That request then inevitably fails. And this is as much as you can do at that point. Without explicit offline support, the browser treats your app as unavailable. And importantly, that will happen either if your static assets are using HTTP caching. It doesn't matter at this point. Thankfully, browsers now ship a set of features called progressive web applications, and some of which here are specifically designed to help with web app reliability and offline experiences. And what we need here is a service worker. A service worker is a script running in your browser on a separate thread that lives between your front-end application and the network and local cache. It can intercept requests, it can cache responses, and serve these responses from users' local cache. And what I just described happens to be precisely what we need to solve our problem. And here is what we'll do. We will create and register a service worker in our application. We will make sure that whenever we are fetching app shell assets, and by app shell I mean HTML, CSS, JavaScript, any static assets that you need for your app to function, service worker will intercept these requests and save these assets in users' local cache, so that when the network disappears, service worker will still be able to serve these assets from the user's local cache. That's the idea. And without diving into specifics of service workers, we've used Vite plugin PWA because we were using Vite's ecosystem. And with this configuration, we get everything that we need in this case. Here we're saying that we want to generate a service worker file. We want this file to be automatically injected into our index.html, into the head tag. And we're specifying a pattern by which the service worker will match requests, again, for any static assets, will cache these assets in users' local cache, and serve these assets cache first. And this is everything that we need. With this, effectively, what we've done is now, when you refresh the page in offline, the browser will serve your local cached version. Amazing. The app works. Now it's time for us to ensure that it can show something meaningful. And here, going back to our builders, they want to be able to view the field nodes that they previously saw when they are offline. And that's our first technical requirement. That is, the app has to be able to read data from local cache. But in order to read anything from local cache, we have to make sure that there is a cache in the first place, and we are populating it with the data that the user is requesting from the network. And it's simplest to do if you're using a single layer through which all of the data fetching happens. It was the case for us, might be the case for you, if you're using something like React Query. So with React Query, all of your front-end code uses queries and mutations that go through React Query and hit the network. Now, importantly and conveniently for us, React Query already has a caching mechanism built in. There is a query cache that sits inside of React Query, and as you're fetching the data, that data is sitting in the cache. What's a problem for us, and a feature here, is that this cache sits in JavaScript memory. So as soon as you refresh, it's gone. You have to start fetching again. But what we can do is we can take that cache and persist it and rehydrate it across reloads. Okay, that's a simple idea. But before we do it, we need to know where to store it. And here browsers give us a few different options we can choose from. Two simplest ones being cookies and local storage. I'll just mention that these are either not designed for this purpose or too limiting or otherwise constrained. So I would go straight to IndexedDB. An IndexedDB is browser API for client-side transactional database. And importantly for us, it has the following characteristics. It's asynchronous, so writing, reading from it doesn't block the main application. It has large storage limits, gigabytes or even more. And it has good support for various data types. It can store arrays or objects, but it can also store blobs or files. All of these make it very, very nice fit for storing large amounts of data that we have fetched from the API locally. So here's what we'll do. We'll persist the query cache. We will use IndexedDB for it, and we will apply selective persistence. And I'll start with the last. As I mentioned in the beginning, we don't need every feature that this app has to be available offline. And thus, we probably don't need all of the data that the user has fetched to be persisted in IndexedDB. So here we've got an example function that takes in a query from React Query, and based on the query key, so like a query name, it decides, do we want to persist it or not? And for us, for our application, we need all of the data that's needed for the entire app to function. So all of the global data. For us, that might be something like a user context. And then you need all of the data that's on the critical path to the features you want to have supported offline. Again, for us, it was something like list of field nodes or field node details. And that's our selective persistence. React Query has a cool plugin called React Query Persist Client, which, surprise, surprise, can persist the client, and the client contains the query cache inside of it. It requires us to implement this interface that will persist the client somewhere and restore it from somewhere. And that somewhere is our decision. We've decided to use IndexedDB, so we pulled in another library called IDB keyval, which creates a simple key value store in the IndexedDB, and the persister will persist the client there and restore it from there. And here's how it all comes together. We also get a persist query client provider component, which basically replaces your regular query client provider. We pass in the persister, the selective persistence function, and with this, what we've effectively achieved, as the user is interacting with the app and fetching the data, it sits now in the query cache. We take the data that's needed offline, and we store it in IndexedDB, so that when the user disconnects, we can still rehydrate that query cache because data is sitting in IndexedDB. And that's it. With cached data is now available when the user is offline. Happy days. And the final thing, the final boss, mutations. And that's the second technical requirement. Our app has to be able to write to a local queue. And here's the idea behind the queue. As our builders are working in a field and making a bunch of updates, they want to update the field node status. Maybe they fixed the window, they want to update the field node, and we will store that intent as an item in the queue. They make another change, we will add another item to the queue, another change, another item added to the queue. We don't want to lose this data, so we will also store it in IndexedDB separately from the query cache. And all of this so that we can, when the user reconnects, take all of these items from the queue and one by one replay them and basically issue network requests based on the items that are sitting in the queue. And here's how we've done it in practice. We've implemented a queue class without diving into specifics. We can add the items to the queue, we can remove the items to the queue, they will be persisted at IndexedDB. And finally, we can call sync on the queue. And what the syncing does, it takes the item by item from the queue and processes them. I will show what that means in a bit. We provide a single instance of that queue to the entire React tree using a provider pattern. And here is where the processor function comes in. Like I mentioned, during sync, we take each item and process it. And by processing, in our case, what we do, we just call the correct API endpoint to change the status. Here's an example mutation, and again, based on React Query, and it does one of two things. When the user is offline, we are adding a new item to the queue. We are storing that intent, the ID of a field node and the status the user wants to change it to. But if the user is online, we just issue the network request right here and there. And last bit that we need is we need to kick off that syncing process at some point, and that will happen when the user goes from offline to online. And with all of this, here is how it comes together. The user is online, they make a bunch of changes, they go straight to the network. We call our API. When they disconnect, they can still make changes, but now we will store them in the queue as pieces of data. We don't want to lose it, so we will also persist it at IndexedDB. And all of that, when they reconnect, we take these items from the queue and one by one issue network requests based on them, essentially making these updates available for others to see. That's the idea behind the queue. And with this, mutations are queued and replayed once the user reconnects. And to wrap it all up, what we've achieved here is that app shell is cached using a service worker. Data is available offline because we've cached the entire React Query client. No work is lost because any changes that happened offline, we are storing in a queue in IndexedDB and replaying these actions once the user reconnects. And importantly, we've done all of this with the same code base, the same tech stack, and the same team. That's huge cost-saving potential. Real world is a bit more complicated. That what fits into a 20-minute presentation. So here's a list of things that I haven't covered, but you probably should. So this solution will only give you access to the data that the user has fetched. It might make sense to prefetch a bit more if you know that the user is expected to go offline, and there are a bunch of strategies you might want to dive in there. IndexedDB and the storage there is plentiful, but not infinite, so make sure to monitor it on the user's device. Images require special type of treatment because URLs will no longer work. Be careful when your API changes, because you have to adjust your front-end code, but now there's another place you need to take care of, and that's the local data that sits on each user's device. This is now stale, so you either have to migrate or invalidate it. Queue requires a bit of hardening, so what we've done is we've implemented retries and sync pausing. And finally, there is a point where you need to seriously invest into proper conflict resolution, handling request idempotency, and there's a whole backend component that comes in here. And like I hinted at in the very beginning, if you need true background processing, tight OS level integration, hardware access, or support for even larger data sets, you do need to reach out for a proper mobile solution. So web can do a lot for you, but there is a point beyond which a proper mobile rewrite is definitely needed. But I hope, all in all, that it proves that offline is a product requirement, not a platform requirement. And I want to end with a few takeaways. First, listen to your users. We've learned that our app doesn't really work best in places and conditions where our users need it the most. So maybe try using your app in the places and situations where your users are most frequently using it in. You might realize that they would really benefit from having some of the functionality available offline. And if they do, try this process out. We've made a bunch of trade-offs that make this process reasonably straightforward to implement, but it can drastically improve the user experience. And finally, make sure to let the requirements drive technical decisions, especially before you embark on a costly rewrite. And that's it. I really appreciate the attention. Thank you very much.
Thank you. Okay, let's pick up and move to the seats over there. You want to grab your stuff? Okay. There you go. All right. There's a lot of traffic and questions. This is going to be fun.
I'm not sure if that's
and yeah, so while we're at it, you convince people to move some of the app functionality offline. And the biggest question here, it has like 10 upvotes or something, is that what the strategy is for then reuniting the data when people are back online. So the question specifically says the strategy for last write wins has limitations. And I'm going to maybe go through the question a bit more later. But what's your recommendation to people? How did you handle it before? How do you think about the transition from always online to then having to recombine the data afterwards?
So like I said during the talk, this is a thing that we've done in the first iteration because that required essentially no work. But beyond it, it will depend on your particular use case because this mutation was a simple example, but it won't apply to other cases as well. So there are different things you can do. Some a bit more naive, like maybe it's enough for you to, before you actually make the sync, so before you issue the network request, try to hit the API first and see if the status didn't change. It won't solve the concurrency problems, but it will help definitely. Other than that, you need to invest in a proper solution that spans across front-end and back-end, which is like maybe you send a snapshot of the status first, and when you make the change, you send both the previous value and the new value, and then your backend needs to figure out, is there another change that happened at the same time? and basically resolve it from there. But I guess it depends, like, case by case.
Yeah. But this is a very good entry point to figuring out that problem. And if someone wants to be really serious about it, I guess all we can say is 4 letters, CRDT.
Yeah, well, that's a topic for a separate
for a separate conference or two. Okay, so next up is going to be a bit simpler. What's the best way to inform the user that they're offline and someone says that they had issues with navigator.online because it's not always reliable. So how do you detect? How do you prefer to inform the user?
Again, hand wavy in terms of what fits into 20 minutes. Online will tell you that you're connected to something, but that something doesn't have to be connected to the internet. So it doesn't ensure that you're actually connected to the internet. Plus, it doesn't ensure that the connection is good enough for you to proceed. So from what I recall, like the only proper way to 100% know if you have access to the internet is to like ping a health check endpoint that you yourself have. And that's the only like most reliable solution. That's one part of the problem. And second part of the problem, for dealing with small amounts of data, it's not a big issue. But if you're doing heavy requests, then if your user is on 2G, maybe you should say that they are still offline, because that's not good enough for you to proceed the work. So there is also like the entire policy around network quality or network connection quality you might introduce. And Navigator also will expose you some information. It's not perfect, but it's a start.
Yeah. And with all of that complexity, the next thing people want to know is what are your opinions on doing this versus going with a mobile app that you have to install, download from an app store, because it brings in trade-offs, right?
Yeah.
And you mentioned trade-offs, and with those, how do you decide when to choose this instead of going all in with a mobile app?
I would point back to the like product requirements. And to give you an example, this fits nicely with our use case because I haven't mentioned that, but one of the requirements that we wanted to satisfy was specifically not having to ask users to install anything from on their devices. Like to ensure that they are able to use it and forget about it. Sometimes they will use it for a day, for 2 days, for a week, maybe for a month, but we don't want them to go through a hassle of having to install something on their phone. So this fits perfectly here. So I guess it's based on the requirements and goals that you have and want to achieve.
Yeah, this is a good reminder that the best platform for installing apps has already been invented, and it's called the web.
Good point. And, kind of like progressive web applications also allow you to install something on your home screen. But that's another topic because iOS and Android have different approaches to it. And
yeah,
it's easy on Android, not so easy on
Well, you made this segue for me. So the next question is about iOS limitations. Did you hit iOS limitations with the worker stuff and any tips on what to avoid?
Not that I can recall on the service worker level. We'll definitely hit problems with app installation because Android allows you to control that experience from within your app because of the like before install and install events that are triggered, which iOS doesn't want to do because they want to discourage users from installing web apps on their phones because of reasons. You can still do it on iOS, but it requires the user to go into like iOS's native options menu and adding the app to your home screen, which like is unreasonable for me to ask the users to do. So that's the only limitation that I can think of right now. Not specifically with this, but with app installation.
Yeah, but that's a business requirement, so not much we can do about it.
Yep.
Right. I guess that's enough for questions right now. I am going to get you queued for questions downstairs later. So I hope you're staying around because there's questions and some more.
Okay.
I'm not going to have room to ask any more here, but these are some good questions. So bring your questions downstairs later during the break and try to find Tomasz. And for now, thank you for a really good and very important presentation.
Thanks a lot. It was exciting. Thanks.
All right.